relative mass. And in chemistry, it's really hard to sort of observe the mass of some things directly because they're so small, right? Like atoms and molecules. So when we're talking about the mass of something, we're talking about a quantity of matter. And if I compare one object to another, we're talking about relative mass. And we would have to have the same quantity of each substance that we're comparing. So let me give you an example. If I have a staple and a grain of rice, which are obviously very small, if I'm talking about their relative masses, it would be easier if I had the same quantity of each that I was comparing. So if I have 100 staples and I'm comparing them with 100 grains of rice, 100 staples have twice as much mass as 100 grains of rice do. So if I'm comparing the same quantity, then what I could do is I could compare them individually. So 100 staples weigh twice as much as 100 grains of rice. And then I could say that a staple will weigh twice as much as a grain of rice. And this is known as relative mass. And we use this a lot in chemistry. So the mass ratio of any equal number of items equals the average mass ratio of the individual items. Okay, and let's come down here. And let's go to the next page. Let's talk about the law of constant composition. All right, so to use this concept of relative mass, chemists need to be able to weigh equal numbers of different types of atoms. In the 1800s, chemists discovered that all samples of a certain compound, like let's say the certain compound that we're looking at is water, all samples of water would have the same mass ratio of their constituent elements. So anytime they're talking about constituent elements, they would be talking about the elements that make up that particular compound. So in this case, since we're talking about water, we'd be talking about hydrogen and oxygen. So for example, there are 8 grams of oxygen for every 1 gram of hydrogen in every single sample of water. So the ratio would always be 8:1. And this is called the law of constant composition. Okay? John Dalton said that this law supports the concept that atoms exist, but it also provides their relative masses. Okay, so let's take a look at a sample problem. Let's come down here. Here it says a chemist heats 0.35 grams of magnesium powder in a crucible. Then what happens to the magnesium is it reacts with the oxygen gas in the air, and it produces a compound called magnesium oxide, of which we have 0.58 grams. They want to know the mass of magnesium relative to the mass of oxygen. Well, you need to have the mass of each element or atom in that compound in order to do the relative mass. So we have the mass of magnesium, but I need to get the mass of oxygen. And I would do that by subtracting. Okay, we don't always have to do that, but in this case we do. So here they took the mass of magnesium oxide, they subtracted the mass of magnesium to get the mass of oxygen. Now, since in the problem it says we want the mass of magnesium relative to the mass of oxygen, you're going to put the magnesium on top first. So here is the mass of magnesium, and here is the mass of oxygen on the bottom. You would divide them out, grams would cancel, and then 1.52 would be the relative mass. So if you had to state in a sentence what they were in comparison to each other, a magnesium atom weighs 1.52 times as much as an oxygen atom. Done. Okay? Yeah.
When they created the substance, how did they know that only one oxygen atom was attached?
Well, because magnesium oxide would be Mg plus 2 and O minus 2, so you would have to have one of each because the charges add up to 0. Okay? Okay, let's take a look at the practice problems. why don't you guys do numbers 1 and number 2, and let's see what you come up with. Okay, did you guys get that? Any questions for me on those? Turn to the next page. Okay, now let's talk about the relative masses of atoms. So the element hydrogen was originally discovered to have the least massive atoms. So its atoms are actually assigned an atomic mass of 1 U. You should know that this U stands for atomic mass units, which sometimes are abbreviated AMU as well. Now, all of the other masses of the other different types of atoms on the periodic table were expressed relative to this. So if you take a look at hydrogen on that new periodic table that I gave you, okay, you will notice that underneath hydrogen, it should say 1.01. Agreed? Okay. And then what I want you to do is take a look over at oxygen on the right-hand side. Does it say 16.00? Okay, so what this means is the atomic mass of oxygen, which is 16, so the mass of an oxygen atom would be 16 times that of the mass of a hydrogen atom. Okay, if I'm looking at nitrogen, nitrogen on your periodic table says 14.01, yes? Okay, so that means that a nitrogen atom would be 14.01 times the mass of a hydrogen atom. Okay, okay, now, let's move on down here. I don't know that there's anything else we need to discuss. Nope, not on this page. Let's go to the next page, or the last page, where it says Cannizzaro's paper. So John Dalton had assumed that when atoms combine to make compounds, they do so in very simple ways. And there really wasn't any sort of like evidence for his ideas that atoms combined simply. And in 1860, a bunch of chemists got together at a meeting, and there was an Italian chemist by the name of Cannizzaro. He presented a paper where he solved the mystery of atomic masses. And John Dalton didn't really understand how hydrogen and oxygen could combine to make water, because it didn't make sense how water could have 2 hydrogens and an oxygen. So what Cannizzaro did was Cannizzaro showed that hydrogen and oxygen were actually something called diatomic molecules. That means when they're in pure form, they exist as 2 stuck together. And here we are showing you that this would be a hydrogen molecule as 2 stuck together, which would be H2. God bless you. Okay. Same thing with oxygen. In nature, oxygen, as long as it's pure, tends to exist as 2 stuck together. So that means it's usually O2, another diatomic molecule. So when these combine, that's how and then bonds break, that's how we form water molecules, okay? So there are other diatomic molecules on the periodic table: iodine, nitrogen, fluorine, bromine, and chlorine are the rest. Now, there are 2 different ways that make it easier for you to remember which ones are diatomic. On your periodic table, there is an upside down L, Okay, so this is showing you the elements that exist as diatomic elements. If you want to mark that on your new periodic table so you remember, you can. The other way to remember this is info birch. Okay, so these would be all of the diatomic elements. Okay, so this is if they are pure, they exist as two stuck together. If they're in a compound, they may or may not have a subscript 2 on them. That is determined by the charges that they have. Okay, so don't start thinking that everything in a compound would have to be diatomic. Does that make sense? Okay. Okay, that's it for section 3.1.